we'll move to one particular example of a learner, which is basically a decision tree. So I assume Saheli covered decision trees on Saturday, but we don't need to worry about it. So because that's the advantage. We are using decision tree as a black box. We don't need to understand how the decision tree learner works. Just I have to assume that you plug in data to it, and it will return a classifier to you. So that's the only thing you need to be able to know. But still, if you know it, you will realize that it's a very, very powerful classifier. It can fit almost any data and get you 100% accuracy. So, and that's not really always a good thing, because that's a very high capacity learner, and because of that, it's very highly unstable. If you give different subsets, it will learn very, very different classifiers. So that means that it's a very good candidate for bagging. And it's very easy to overfit, and it is difficult to regularize it. Unlike, say, SVMs, it is very easy to regularize SVMs because it's a very stable thing, and it's also there is a convex optimization thing going on behind it, which you can regularize easily by a penalty term. But decision trees are very hard to regularize. I mean, it's very non-intuitive. I mean, you can do pruning, you can restrict the number of nodes and all that, but none of that is very clear that how it has a regularizing effect. So it meets both the criteria. It's very easy to overfit, and it is very difficult to regularize, and it's a highly unstable learner. So it's a very, very good candidate for bagging. So bag decision trees by themselves are very, very powerful. Okay, but there is something which you could do. There is something you could do better. And, well, I want to make bagging successful. So if I want to make bagging successful, I have to make the individual learners as diverse as possible. I want to force it to be different. Not just hope that randomness will do it for me. I can force it to be different. So one reason that many people find that a lot of different learners are often very closely related is because there are maybe a couple of features which are very, very powerful. For example, say you are trying to predict from the demographics of the people who boarded the Titanic whether someone survived or not. Okay, so if you have the gender feature, it's going to be a very, very powerful predictor. So if you have, even if you have, say, if you have 1,000 data of 1,000 people who are boarding there, and even if you chose 500 different, I mean, may say 30 different subsets of 500 people each. But if you had the gender feature, what your decision tree would just simply look at it, gender is going to work. So it will just going to predict gender. And even though you have actually trained it on different subsets, because there is one very, very powerful feature. There is one that's basically the gender. It's not all powerful. It is not going to, not all women survived and not all men died. It is not all powerful feature, but it's still a very powerful feature. If you just use that alone, you would get a very good classifier, but you can do better. So if you if you allowed all the classifiers, all the decision tree classifiers to use this feature, all of them would use the gender feature very heavily. Even though you have trained them on different subsets of the training data, they will use that very heavily. So you can force it to not use it. How do you do that? So you add one more level of randomness, which is to increase the variance. Each individual classifier is learned not only on a subset of the samples, but also on a subset of features. You say, for example, say you have 1,000 people, and say you have 10 demographic features, like maybe their age, their gender, their class, ticket class, and all that. So you have 10 features. The normal bagging, what it would do is it would just select 500. Say in each bag, it would just put 500 of those samples and all the features. That's what a normal bagging classifier would do. But you add one more extra element of randomness, that in each of the bag classifier, not only do you select a subset of the samples, you also select a subset of the features out of the 10. That means that not all the individual classifiers will get the gender feature. There will be, say, at least some classifiers which will have to predict someone survived or not without the gender feature. That means that you're forced to learn something different from the gender feature. So that's the idea, and so it's a very simple algorithm. I'm not going to go too much into detail because the lab session we will actually implement the random forest regressor. So this is the random forest regressor classifier, and make no mistake, this is the most powerful regressor classifier that you will use in any kind of, say, data competition that you go to. This is the first thing that you will use, and it is going to be very, very hard to beat this. Okay. So, but it's a very, very simple classifier. It's when you look at it, it's very, very simple. So you choose number of your classifiers that you want to learn. I mean, that's generally limited by time. You can't learn a million classifiers. I mean, the more, the better, always. That's always the case. But you can't learn a million classifiers. Maybe you have the time to learn only, say, 100 classifiers. So that means that you set, say, number of estimators to be 100. And then you select the typical A, comma B is 0.5. So you can just, for example, for simplicity, you can just set A, B to be 0.5. You select half the number of samples at random for each of the estimator. And you select half the number of features. So if you have, say, 1,000 samples and 10 features, on average, each of the individual decision tree learners would get 500 samples with 5 features each. Okay, so that's on average. Of course, there can be, instead of 500, it can be 550, or instead of 5, it can be 4 or 6. Because there is a randomness here, it can be more or less. But on average, that's how it's going to be. And each of then, once you have gotten that subset of your samples and your features, and then you just let it through your black box. And the black box is going to spit out a classifier at you, and you just store those classifiers. And finally, when you want to make the prediction on a new instance, you just take a majority voting. So all this will hold for also for regression, just that now instead of taking majority voting, you would do an average. That's basically it. So random forest regression is very, very simple. I mean, you have to assume that you have an access to a decision tree classifier black box. If not, that you have to take into account. But if you have black boxes of unstable classifiers which are high capacity, then you can just use a random, or basically bagging along with, bagging just selects samples. A random forest does goes one level deeper and also selects features and uses decision tree classifiers. So that's the 3 components of random forest. Basically, you select samples at random, you select dimensions at random, and your black box classifier that you're using is going to be a decision tree. That's the these 3 components make up random forests. That's basically it. So any questions on this? Yeah, so you'll be implementing this. I mean, there are, if so you will be implementing this in Python. So there are you can just implement it in just one line. So there is libraries out there which can do random forest in just one line. You can do that, but I also want you to understand how it works. So you will also, yeah, you had a question.
This classifier,
Mm-hmm.
how we are going to decide the other parameters like number of splits, depth, and other?
Right. So that's the problem of the black box. You don't worry about it. So the black box is something which you don't touch. Somehow you assume that someone has given you a good black box learner. The advantage with bagging is it kind of takes care of almost everything. So it is very invariant to those kind of things. So if you have a decision tree classifier with even if the decision tree classifier overfits to an extreme extent, bagging will reduce it to an extent. So your important thing is you should not set your decision tree classifier to be too shallow. For example, if you set your decision tree classifier to be just say 1 node deep, then the problem is it's not an unstable classifier. It will, I mean, even if you give different subsets, it's going to predict more or less the same thing, and then your benefit of bagging is going to go away. So the only guideline is you ask the black box manufacturer to make the thing overfit. That's always easy. So the problem is balancing between underfitting and overfitting. If you want to overfit or if you want underfit, it is easy. If you want underfit, you can say always predict 0, always predict 1. That's easy. If you want to overfit, you can just say, yeah, use the class of all hypothesis. That's easy. But that's not, the problem is balancing these two. So what the random forest part or the sampling, the random collection part, what it does is, it does the balancing part for you. It plays the role of the regularizer and it underfits for you. So the job of the black box or the decision tree learner is to simply overfit. So that's the idea. But you can play with those parameters also. Yeah. Yes. Yeah, so that's the thing. So you are, because it's overfitting, you will find, yes. Yes. It might. So I'm not saying it will not. But if if it does, it will overfit much lesser than the original thing anyway. So the bagging will reduce the effect of overfitting. So if you have, Arun, I think, did the bias variance decomposition part of it. So high variance or high capacity learners have very low bias but have a very high variance. And the simplest way to reduce variance is averaging. And that's essentially what bagging does. So, but if you have, let's say, low capacity learners, which have very low variance but very high bias, bagging is not going to help you because averaging is not going to take care of the bias. The bias is going to stay there. But averaging will take care of the variance. So that is the idea. It could happen. I'm not saying it will never happen. So, I mean, for example, it could happen, but it's unlikely. That's what I'll say. So it's, yeah. Any other questions? So if you have no other questions, I'll move to the next part. Oh, I'll just show an example. So for example, this is the data, and you learn a decision tree, it looks like this. So I'll show, say what the real data is. This is the make moons data set, which is basically that you have a red data forming like this and a blue data forming like this. Oh, both are red now, but it's fine. So understand, this is the red data, this is the blue data, and there is noise to it. So this is essentially the true form of the data. And you can see that kind of random forest gets that. You can see a blue curve here and a red curve here. But decision tree does not, I mean, it tries to overfit too much, and you can see very strange patterns. I mean, of course, both the things get right, this corner here, it's easy. The problem is the central part, where you have to be careful, and random forest does a much better job of doing it than decision trees. So just an example of how it would finally look like. So you can see that decision tree looks neater. It's like there is only a small number of colors. So just blue, red, and white, and yellow. But random forest looks all over the place. That's because of averaging. Even if you have classifiers which are always going to predict 0 or 1, if you average 100 of them, you will get different majority votes, right? I mean, say for one instance, you will have maybe 70% predicting positive. And for another instance, you might have 63% predicting positive. So that means that you get all the range of all possible values, not just 0 or 1. You get everything from 0 to 1. So that's why you will see a lot of different colors, I mean, different shades of blue. That's basically because you will see, for example, what that means is, here in both cases, both in this area and this area, the blue is the majority. But here it's a much more overwhelming majority than here. So here, maybe I'm giving an example. Say maybe you learned, say, 30 classifiers. In this area, all 30 of them agree. But maybe in this area, you only find that, say, 20 of them agree. 20 of them say it's blue, and 10 of them say it's red. That's why it's, and say in the white areas, it's very, very close to random. So that's the white. The white is basically indicating almost close to 50%. So, and that's kind of nice in the sense that the white area is here. I mean, there is a white area here, but ignore that. There is a white area here, which is what you really want. I mean, this area is really the most uncertain area in reality. I mean, you can't do much better than that, and it is kind of getting that. So that's the, you can't do better than what, even if you knew the distributions, you can't do much better than this. So that's the idea. And that's what, this is just, you will actually implement these and you'll see these plots yourself, so it's not a problem. Okay? Yeah. So we'll move on to the next paradigm, which is sequential ensembles. Now we have done with the parallel ensemble, so it means that every learner you have learned in parallel. So you can clearly see that random forest also you can learn in parallel. So if you are learning, say, 30 or 40 decision trees, you can learn each of them in parallel. That's not a problem. Now we'll move on to sequential ensembles, where you can no longer do that. You will have to use the previous classifiers. Okay. So the example is boosting. So it works in a completely different paradigm. So they are both ensemble methods, but say the cases where they work is completely different. So you can start afresh if you want. So it's a completely fresh thing. Okay. So so the idea is each model built in the ensemble explicitly uses the other models. Okay. Okay. So where is the motivation for boosting? So once again, it comes from a black box kind of access, but you have a black box which is very weak. That's the idea. So it's kind of very opposite of what you had in bagging. In your bagging, each of the individual learners was very high capacity. It could fit arbitrarily well. But here in boosting, you have individual learners which are very weak. Say, for example, each of them just decide based on one feature, maybe. That's the simple. I mean, you might have 100 features, but each of your individual learners is going to decide positive or negative based on just one feature. It's an extreme case, but that's actually a very powerful case in itself with boosting. That's what we'll see. And that's the idea. So each of the individual learners are very weak. Say, what do I mean by weak? You can only do slightly better than random. So 50% you can always do. I mean, you can always toss a coin and get 50%. That's not a problem at all. But you are saying that you have access to a black box learner, and you can only say that black box learner can guarantee it's slightly better than random. That's the only thing you can guarantee. Now, the idea of boosting is, can you combine these multiple weak learners, weak models, into one strong model? So a parallel strategy or oblivious strategy, I mean, where you build each model without being aware of what the other models are doing, is not going to be very successful here. The idea is that each new weak classifier you are going to build is going to have to make up for the weaknesses of the previous classifiers. Each of the new thing is going to be weak, but it's going to be weak in a different area. So that overall you would be strong. So that's the idea. For example, the standard terminology we'll use here for us is basically experts. Like, it's a mixture of experts. This is a paradigm called a mixture of experts, and this is something which you will often see. Why is it called a mixture of experts? Say, for example, if you are the prime minister and you want to decide on policy. I mean, you can't ask randomly good people. So essentially, you hire one economic advisor. He's not going to be very good at deciding foreign policy for you, but that's why you hire a foreign policy advisor. And then you hire maybe a labor advisor, and so on. So you hire different people who are very strong in their area. But if you use them for everything, you're going to fail. You can't, if you use your foreign policy advisor for deciding economic RBI rates and so on, you're going to fail horribly. So it's essentially, you bring in your experts which have different areas of expertise and combine them together. So that's the idea behind boosting. So how does that work? For example, say you first asked to learn a first classifier, and then you find that, say, it is kind of doing well in one area. So you say, okay, I'm doing well in this area. I want to somehow focus on the other area. So that's the broad idea. You will actually see a very good example now in the future. Okay. So what is the key idea? The key idea is that the weak learners are given weighted training samples. That's the key idea. All the examples that you have seen before, training samples all had equal weight. All samples had equal weight. There was no, training sample 1 was the same as equally important as training sample 35. That was the case. But here the weak learners are given weighted. So is that such a big deal? I mean, you can always simulate weighted training samples by adding. I mean, I can say, for example, the case where I have x1, y1, x2, y2, as this has a weight of, say, 2 and this has a weight of 1. I can always simulate unweighted thing by having just x1, y1, x1, y1, and x2, y2. I've repeated x1, y1. So now everything has equal weight of 1. So I can simulate a weighted training data by unweighted training data by just repeating things. But it makes life simpler if you view weights directly. So that's the idea. So now you can have, that means that now you have the first sample is more important than the second sample. So that's the idea. So that's the first idea. And the next idea is the weight of the sample depends on how previous weak learners have done on that sample. For example, say if you have a sample, and if you are now deciding the 11th classifier in your series sequence, okay? Now if you have a sample on which all the 10 classifiers have done pretty the right thing. Now, the 11th classifier, it does not really matter if it gets this particular sample right or wrong, because anyway you are going to combine things so that this is going to do well. So that means that the weight of this particular sample, which all the previous things have done well, will be very low. And you say you have another sample which all the 10 classifiers have gotten wrong. Okay, that means that it is crucially important that now this new classifier gets that right. So that means that weight will be higher. So that's the essence of the idea. Yeah. Yeah. So essentially, basically, what you do is, say you have one training sample or one sample which all your 10 previous classifiers got correctly. Okay, that's the case. Then now when you are building the 11th classifier, that's what you're doing now. When you're doing the 11th classifier, it does not matter if you get this sample right or wrong, because anyway, when you are combining it, the majority is going to work. because even when you are finally going to take the majority, on that sample it's going to work. So it does not matter whether you get that sample right or not. And you have another sample, say another sample, where all the 10 classifiers got wrong. Now it's very important that you get that right. In the 11th classifier, it's important that it gets it right so that it can counteract for the weakness of the other 10 classifiers. So that's the essence of the idea, it's the philosophy. So you will see a good illustration here. So the algorithm has a lot of details, but don't need to, I'll show the algorithm first. Don't get intimidated by it in the first glance, and then we'll run it through an example, and I'll show the algorithm again. So you will see that it's not really that complicated. So what you need is basically a gamma, which is often called the edge. So you need to know that the weak learner is going to do at least 0.5 plus gamma. If it's going to be if gamma is going to be 0, then it's useless. I might just as well toss a coin and do it, right? There's no need for me to do. So that means that I need to build a boosting principle. You need to be able to guarantee that your weak learner is going to do at least as well as 0.5 plus gamma. So the gamma can be arbitrarily close to 0. It can be 0.001. It can be 0.001. It's not a problem, but it should not be 0. So that's if gamma is already 0.5, then you are done. Why bother combining things at all? You already have an edge of 0.5. You might just get one weak learner and be done with it. So the typical case would be something like maybe you would have gamma to be maybe 0.01 or something like that. So that would be a typical case. You have weak learners which can do slightly better than random. Okay, so that's the idea. And you need that gamma. And you convert that gamma to a beta. So this beta you will see is basically how you reweight the samples. So we'll get to that later. So you have your samples which are basically either negative data or it's classification again. So each instance is either negative or positive. And then your weak classifier also does that. So so this is called a weak classifier. So a weak classifier returns, it takes in an instance and gives -1 or +1. That's what it's going to give. Okay. So what the edge is saying is that each of your weak learners is going to get at least 0.5 plus gamma accuracy. That's what it is saying. Okay. So what is the algorithm? The algorithm is simple. So you initialize with equal weights for every sample. So that's the weights for the initialization. You give equal weights to all the samples. That's the sensible thing to do. If you have not learned anything, so it makes sense to have equal weights to everything. And then say you are building T of these learners. So you learn HT, which is a weak learner. You use your entire training sample S, and you use the weight of that current iteration. So the first iteration is going to be equal weights. It's not a problem. And then for every sample I, you see whether you've got it right or not. So HT of xi is going to be either +1 or -1. And yi is also going to be +1 or -1. So HT of xi, if HT of xi is equal to yi, then this is going to be, so this essentially, you can have it a simpler thing, would be indicator of HT of xi equal to yi. I've done this because it's actually more general, but this is perhaps easier. So your LTI is simply saying, in the tth iteration, did I get my ith sample right or wrong? So the loss incurred by the tth classifier on the ith sample, that's your LTI. Okay? And now if LTI is 1, that means that I need to increase the sample of weight of sample I. And so that's what I'm going to do. So that means that beta is 0.5 plus gamma by 0.5 minus gamma. So beta is going to be greater than 1. So because gamma is going to be greater than 0, beta is going to be greater than 1. So what will happen at the end of the iteration is, the weight of the ith sample at the t plus 1th is going to be simply, I'm going to take the weight of the sample I at the tth iteration, and I'm going to multiply by beta if it has gotten the ith sample wrong. So for example, say at the tth iteration, say the weight of WTI, WTI was say maybe 3. I'm just giving some arbitrary number. And at the ith iteration, now your, at the tth iteration, say your yi was basically +1, but your ht of xi was -1. So that means that the tth weak learner that you learn is wrong on sample I. Okay, that's what it is. That means that at the end of the iteration now, your weight of the ith sample is going to increase. So that means that at the end of this, now your WT plus 1 I is going to be 3 beta. So beta is going to be greater than 1. That means that the weight of the ith sample is going to increase. So all samples which for which you have the wrong answer at this iteration, the weight is going to increase. Otherwise, the weight is going to stay the same. So we are never going to reduce the weights. The weights is always going to be increasing only. So that's the idea. And then you're going to use these weights in the next iteration. So that's the idea. So that's kind of captures the intuition. So if your teeth weak learner gets the ith sample wrong, then the weight of the ith sample increases. That's the idea. So just illustrate it with a good example, okay?